Welcome back to QHSE Talks. There's a question every safety professional has heard, sometimes out loud, sometimes between the lines. Is this really unsafe? Or is the worker just not used to it yet? That question sits right at the center of manual handling injuries. Because unlike falls or fires, lifting injuries don't feel catastrophic in the moment. Nothing breaks, nothing explodes, production keeps moving. And yet, year after year, low back injuries and musculoskeletal disorders remain one of the largest loss drivers in industry. Not because we don't care, but because for a long time we didn't have a defensible way to measure them. And that's where CSP Chapter 24 Ergonomics changes the conversation. This chapter lives squarely in advanced safety application because it forces us to stop treating manual handling as normal work and start treating it as a materials handling system, one that can be evaluated, quantified, and redesigned. Think about how we normally approach risk. If it's a crane, we ask, what's the load rating? What's the radius? What's the margin? If it's a forklift, we look at capacity, center of gravity, attachment effects. But when the lifting device is a human being, historically we asked almost nothing. We assumed adaptability. We assumed toughness. We assumed experience would compensate for physics. Chapter 24 challenges that assumption directly. It says manual handling is not a character test. It's a design problem. And once you accept that, everything changes. Because now, ergonomics becomes part of materials handling evaluation, not an afterthought. It becomes part of prevention through design, not post-injury correction. And it becomes a risk management activity, not a comfort initiative. This is why the revised NIOSH lifting equation matters so much. Not because it gives us a number, but because it gives us authority. It allows a safety professional to look at a task and say, this lift exceeds the system's capacity. Not emotionally, not subjectively, mathematically. And more importantly, it shows why. Is the load too far from the body? Is the origin height too low? Is there excessive vertical travel? Is twisting being designed into the task? Is frequency quietly pushing the body past recovery limits? Is the tool or container itself poorly designed? Those aren't training issues, those are engineering inputs. And Chapter 24 doesn't stop at calculation. It pushes us into job hazard analysis, asking us to document geometry, frequency, coupling, and posture the same way we would document energy sources or failure modes. That's the philosophical shift. Instead of asking, how do we teach workers to survive the job? We ask, how do we design the job so survival isn't required? Because the moment you accept that the human body has load limits, reach limits, and fatigue limits, ergonomics stops being optional. It becomes unavoidable. And that brings us to the heart of this chapter and to why this topic resonates so deeply with safety professionals.
The invisible math of safety. And look, I know ergonomics has a bit of a branding problem.
It does.
It sounds like something HR talks about to justify buying those expensive mesh chairs.
Right. Or a weird-looking mouse.
Exactly. But looking at Yates's breakdown here, it's so much more than posture. It's physics, it's biology, and it's basically hard-limit structural engineering, but applied to flesh and bone.
It really is structural engineering, and I think the reason this chapter resonates and why so many people ask for a long explanation is that it represents this fundamental shift in philosophy.
How so?
Well, you go back 50, maybe 60 years, and the management theory was always, here's the job, it involves lifting 100-pound sacks, find me a worker who's tough enough to do it.
And if they break?
Then they weren't tough enough, find a new one. But Chapter 24 completely flips that on its head. The definition Yates gives is designing the job to fit the worker.
Not forcing the worker to fit the job.
Exactly. It's the realization that the human body has a spec sheet, just like a forklift or a crane. If you exceed the load limit or the range of motion, the machine fails. It's not about toughness. It's about hitting mechanical failure points.
So let's open up the spec sheet for this biological machine. The text starts with this concept of the neutral body position. It sounds a little bit zen, but it's actually purely mechanical.
It is. Think of neutral as the position of maximum mechanical advantage and minimum stress. For a human, that's standing upright, arms hanging loosely, elbows close to the body.
Okay.
In that position, your spine is stacked perfectly vertebra on vertebra. The discs are cushioning evenly, the ligaments aren't being stretched. This is your 0 point, your baseline.
So every time we move away from that, just reaching for a coffee cup or bending to tie a shoe, we are technically leaving the safety zone.
You're entering a penalty zone.
Right.
The further you deviate, by reaching out, by twisting, by crouching, the more mechanical leverage you lose, and the more internal force your body has to generate to compensate.
And that, I'm guessing, is where the math starts to get you.
That's where it starts to kill you.
Which brings us to the absolute beast of this chapter, the Naos lifting equation. The text presents this as the gold standard for analyzing manual handling. But before we get into the algebra, who is this actually for? Because Yates puts a specific disclaimer on the scope.
He does, and it's a crucial disclaimer that a lot of people miss. The Nash equation applies to nearly all healthy workers. It assumes you aren't coming in with a pre-existing injury.
Okay, that makes sense.
And crucially, it's designed for lifting tasks that happen over a substantial period of time, up to 8 hours.
Right, so it's not asking, can you lift this heavy rock once to save a puppy?
No.
It's asking, can you lift this rock every 10 minutes for 20 years without completely destroying your L5S1 disc?
Precisely. It measures the chronic exposure to that physical stress.
Okay, let's look at the formula itself. And for everyone listening, don't worry, you don't need a calculator, but I want you to just visualize this. The goal is to find the RWL, the recommended weight limit. And the formula is RWL equals LC times HM times VM times DM times AM times FM times CM.
It looks like the code to launch a nuclear missile.
It really does. But as I was reading through Yates's explanation, something just clicked for me. It's not really a math problem, it's a penalty system. You start with a perfect score, and then the universe just tries to whittle you down to 0.
That is the perfect way to frame it. You start with the LC, the load constant. That is your maximum theoretical potential under, let's say, divine, perfect laboratory conditions.
And Yates gives that load constant as 51 pounds, or 23 kilograms. Now, I have to stop here, because 51 pounds feels kind of low.
Right.
I mean, we have listeners who deadlift 400 pounds for fun. In an industrial setting, you see guys tossing 80-pound concrete bags around. Why is the absolute ceiling set at just 51?
That is the most common objection a safety pro will ever hear. I can lift way more than that. And sure, you can. You can also redline your car's engine to 8,000 RPMs.
But you can't drive it like that all day.
Can you drive it like that for 8 hours a day, 5 days a week for 30 years? The engine blows.
The engine blows.
The 51-pound limit is based on deep medical research into the compressive force on the spine. Specifically, the amount of pressure that begins to cause microfractures in the vertebral end plates.
So it's not about muscle, it's about bone.
It's about bone and disc integrity. Above 51 pounds, even with perfect form, the risk of chronic degeneration just skyrockets for the general population. So 51 is the ceiling. If you have a dox that weighs 60 pounds, the equation stops. It's unsafe, period.
Okay, so we start with 51 pounds in our safety bank account. Now we have to run the gauntlet of these multipliers, the penalties. Let's go through them one by one, because this is where that invisible math really starts to show up. First one is HM, the horizontal multiplier.
This is the distance from your hands to the midpoint of your ankles. So basically, how far away from your body are you holding the thing?
And the math here is just brutal. The formula in the US system is 10 divided by H, where H is the distance in inches.
Right.
So if I hold a box tight to my stomach, let's say it's 10 inches away from my ankles, 10 divided by 10 is 1. I keep my full 51 pounds.
You're good. You have perfect leverage. The multiplier is 1, no penalty.
But what if I just reach out a little bit? You know, say I'm lifting a box off a pallet and I can't get my feet under it, so I'm reaching out maybe 20 inches.
Now you're dealing with the fulcrum effect. Your lower back is the pivot point. The weight is the load. By doubling that horizontal distance to 20 inches, the multiplier becomes 10 divided by 20, which is 0.5.
I just lost 50% of my capacity.
Instantly. You went from a safe limit of 51 pounds to 25.5 pounds. And here's the biological kicker. The box didn't get heavier.
No.
But the torque on your spine just doubled. To your intervertebral discs, that 25-pound box at arm's length feels exactly the same as a 50-pound box held close to your body.
That is absolutely wild. It explains why people hurt their backs picking up light things, like a pencil or a piece of paper, when they reach for it awkwardly.
Yes.
The weight of the object doesn't matter nearly as much as the lever arm you're creating.
You're just magnifying the force against your own internal structure. It's physics.
Okay, next up in the penalty box is VM, the vertical multiplier. This is all about where the hands start the lift.
This is the sweet spot. Yates identifies a neutral zone where this multiplier is optimal, which is basically knuckle height. For most people, that's about 30 inches off the floor.
So if I'm lifting something from a table, I'm probably in a good spot.
You're in a great spot.
But what if I'm lifting it from the floor?
You take a penalty. Lifting from the floor requires you to shift your center of gravity and engage the weaker muscle groups of the lower back just to initiate the movement before your legs can even take over. The equation penalizes you for every inch you are below or even above that 30-inch knuckle height.
So this basically validates every safety poster ever made that says, lift with your legs, not your back. But it actually puts a number on it.
It quantifies it.
If I pick up a box from the floor versus a table, I might lose, 15 or 20% of my safe limit just because of the starting altitude?
Correct. And the same thing goes for lifting overhead. If you're grabbing something off a high shelf, the VM penalty kicks in hard because now your shoulders are in a structurally compromised position.
Then we got DM, the distance multiplier. This one tracks how far the object travels vertically.
You can think of this as the work component in physics class force times distance. Lifting a box 10 inches is one thing. Lifting it from the floor to a shelf 6 feet up. That is a massive energy expenditure.
And I found a fascinating hard stop in the text here. It says if the vertical travel distance is greater than 70 inches.
The multiplier becomes 0. The equation basically says, I don't care if the object is made of styrofoam. If you are lifting something from the floor to nearly 6 feet in the air in one continuous motion, the biomechanical stress of that range of motion is inherently unsafe.
So the recommended weight limit becomes 0.0 pounds.
0. It's a design failure right there. If you have a job that requires that reach, you failed before the worker even clocks in for their shift.
That's a powerful way to put it. Okay, now we get to the villain of the story, the one that I think probably destroys more backs than anything else. AM, the asymmetric multiplier.
The twist.
The text is incredibly harsh on this one. It says, quote, asymmetric lifting should be avoided whenever possible.
Yeah.
Why is twisting so catastrophic for the spine?
Okay, picture your spinal discs. They're like little jelly donuts. A tough, fibrous outer ring called the annulus, holding in a gel-like center.
Okay.
They are fantastic at handling compression, that straight up and down squishing force. They are terrible at handling shear forces.
And shear is the twisting motion.
Right. When you twist under load, you are essentially grinding the fibers of that outer ring. It's like using a mortar and pestle. You are grinding those disc layers against each other, and they are just not designed for that.
The penalty numbers that Yates provides here they're sobering. Let's say I'm doing something pretty standard. I'm moving a box from a conveyor belt in front of me to a pallet over on my right. That's about a 90-degree twist.
Yep. At 90 degrees, the multiplier drops to 0.71.
So I lose almost 30% of my strength just by turning my shoulders.
You do. That 51-pound max just dropped to about 36 pounds. And remember, that's if you do everything else perfectly. If you reach out, that's an HM penalty, and you twist, that's an AM penalty. You are multiplying fractions. You're taking 0.5 times 0.7. Suddenly, your safe limit is down to like 12 pounds.
Wow. And what if I go even further? I mean, we've all done that reach into the back seat of the car maneuver. That's got to be, 130, 140 degrees of twist?
The text draws a very clear line in the sand. If the angle of asymmetry is greater than 135 degrees, the multiplier is 0.00.
0. Again.
It implies that structurally, the human spine cannot safely bear any load at that angle. You are relying entirely on the tensile strength of your ligaments, which is just a recipe for a rupture.
That's the snap moment.
Yeah.
It's not bad luck. It's that you hit the 135-degree cliff and the math just went to 0.
And your body paid the price.
Okay, let's round out the last couple of multipliers here. We have FM, the frequency multiplier. This seems to handle the fatigue factor.
This is all about metabolic recovery. If you lift a heavy box once, your muscles have time to flush out the lactic acid and reoxygenate. If you lift it 10 times a minute, the muscles become hypoxic. They literally run out of oxygen.
And when muscles fail?
They stop protecting the joints in the spine. The load shifts directly onto the passive structures, the ligaments, the bones. The FM drastically reduces the allowed weight as the pace of work increases.
And finally, CM, the coupling multiplier. This is about your grip.
A really simple concept. How hard do you have to squeeze? Good coupling is a box with nice, comfortable handles. Poor coupling is a sagging bag of dog food. or a greasy sheet of metal.
So if I have a poor grip, I have to squeeze harder to control the object.
You do. And that tension radiates. To grip harder, you tense your forearms, which tenses your biceps, which tenses your shoulders and your upper back. You are creating this pretension in your body before you even move the weight. That reduces the amount of external load you can safely handle. The math penalizes you for not having good handles.
So we take all these penalties, distance, height, twist, frequency, grip, a tep. We multiply them all together and then multiply that by 51 and we get the RWL.
That's your recommended weight limit.
Let's say after all that bad news, the RWL for a specific job comes out to be 15 pounds.
Okay, 15 pounds. That is the safety threshold for that specific task.
But the box the worker actually has to lift weighs 30 pounds.
Now we get to the final step. We calculate the lifting index, or LI. This is the simple ratio of reality versus the math. It's the actual weight divided by the recommended weight limit.
So 30 divided by 15.
Equals 2.0. Your lifting index is 2.0.
And what does that number 2.0 actually tell a safety manager?
If the LI is under 1.0, you can probably sleep easy. The task is generally safe for most workers. If it's over 1.0, the risk begins to increase. But once you start seeing numbers like 2.0 or 3.0, you are well into the danger zone.
So it turns a subjective feeling like, that seems heavy, into a hard number.
An objective risk metric. Yates notes that many companies set a hard internal limit, like an LI of 1.5 or 2.0, where they are absolutely required to intervene.
And intervene means redesigning the job, not telling the worker to be more careful.
Right. You don't train the person, you change the physics of the task.
Let's see this in action. The book has some great case studies that play out like little ergonomic detective stories. I want to look at case study 1. The punch press operator.
This is a classic industrial setup. The operator is handling small metal part stock and feeding them into a press. It's highly repetitive work.
And on the surface, it seems fine. The parts aren't massive boulders or anything. But when you run the numbers, the LI at the origin, so where they pick the part up, is 2.7. And at the destination where they place it, it's 3.0.
That's a massive red flag.
A 3.
An LI of 3.0 means the physical demand of that task is 3 times the recommended safe limit. It is a near certainty that this worker will develop a shoulder or a back issue over time. It's just a matter of when.
So how do they fix it? They can't make the metal parts any lighter.
No, but they can change the geometry of the workstation. The analysis in the text points out the big flaws. First, the horizontal multiplier was terrible. The worker was reaching way too far to grab the parts.
Penalty.
Second, the vertical multiplier was off the destination shelf, was way too high, forcing them to lift in place above that sweet spot.
Another penalty.
So the fixes listed are basically engineering controls, bring the pallet closer, and lower the shelf.
Sybil cheap fixes. But there was one more subtle one in there that I loved. It said, modify the job so significant control isn't needed at the destination.
Oh, that's a brilliant one.
Explain that. What does that mean?
Think about the difference between, say, tossing a dirty shirt into a laundry hamper versus threading a needle. When you have to place something very precisely, you have to slow down at the end of the movement. You hold the weight in static tension while you line it up. That dramatically increases the time under tension for the muscles.
I see.
By adding something like a chute or a guide rail so the worker can just drop the part into place, you remove that static hold. The math improves immediately because the task is now dynamic, not static.
That's brilliant. So it's not just where you put it, it's how you put it.
Exactly. The precision of the placement is its own ergonomic factor.
Case study 2 is the one that really hurt my back just reading it. Loading bags into a hopper.
The classic windshield wiper scenario.
Paint the picture for us.
So you've got a worker who stands in one spot. To their left is a pallet of, say, 50-pound bags. To their right is a large hopper they need to fill. They twist left, grab a bag, twist all the way to the right, and dump the bag. And they repeat that for 8 hours.
They never move their feet.
They plant their feet like they're in concrete. And by doing that, they are maximizing the asymmetric multiplier penalty on every single lift. The analysis gives this task an LI of 2.1.
2 times the safe limit, over and over. And the fix seems almost, too stupid to be true. The text just says, reduce the angle of asymmetry.
Which is the technical way of saying, step your feet.
Just move your feet.
If the worker simply pivots, moves their left foot to face the load, picks it up, then steps with their right foot to face the hopper, the twist angle drops to almost 0. The AM multiplier goes from a huge penalty like 0.7 back to 1.0.
It's amazing because it highlights this weird biological paradox. We're inherently lazy conservators of energy. It costs metabolic energy to lift your feet and step. It feels easier to just twist the torso.
We save a single calorie of metabolic energy by not stepping, but we pay for it with hundreds of pounds of destructive shear force on the spine. The math proves that our perceived efficiency is actually biologically expensive in the long run.
Now, we spent a lot of time on lifting boxes and bags, but Yates devotes a significant portion of this chapter, and I want to spend some real time here because the listener specifically asked for it, to the tools for non-listing tasks, this alphabet soup of RULA and REBA.
Yes, because if you work in a call center, or you're a dentist, or you're on an assembly line soldering tiny circuit boards, you aren't lifting 50 pounds, but you are still getting hurt.
So let's differentiate these two tools. RULA, Rapid Upper Limb Assessment.
RULA is designed for sedentary or standing jobs where the upper body is doing pretty much all the work. So think office workers, cashiers, lab technicians, or that soldering example. It focuses strictly on the neck, the trunk, and the upper extremities, your arms and your wrists.
And how does the math work here? It's obviously not the lifting equation.
It's a scoring matrix. An observer watches the worker and assigns a score to different body parts based on their position. For example, you look at the upper arm. Is it hanging neutral, close to the body? That's a score of 1.
The best score.
Is it raised 45 degrees? That's a score of 2. Is the shoulder shrugged up? You add another point.
So like in golf, a low score is good.
Exactly. You want a 1. You sum up the scores for what it calls Group A, the arms and wrists, and Group B, the neck, trunk, and legs. Then you cross-reference those two scores in a grid to get a final grand score.
And this grand score then triggers an action level.
Right. An action level of 1 or 2 means the posture is acceptable. An action level of 3 means investigate favor. Changes may be needed. But an action level of 4, which corresponds to a high grand score, means investigations and changes are required immediately.
I love that the text puts that urgency on it. It's not, think about it next quarter. It's, this person is actively damaging their body right now.
It gives safety managers the ammunition they need to go to management and demand budget. It's not an opinion anymore. It's, we are at action level 4. We need new adjustable desks today.
Okay, so that's RULA for the upper body. How does REBA differ? Rapid Entire Body Assessment.
REBA is for dynamic whole body tasks. Think of a healthcare worker helping a patient out of bed. They are pulling, squatting, twisting, and using their legs and their entire body. Or a mechanic crawling under a truck. RULA doesn't really care about the legs. REBA absolutely does.
So the scoring works in a similar way.
Similar logic, yeah. Group A is the trunk, neck, and legs. Group B is the upper arms, lower arms, and wrists. But REBA adds a crucial load force score and a coupling score, which is very similar to the Nyos-Heish equation. It acknowledges that when you're moving your whole body, you're usually moving some kind of weight, too.
So if I'm analyzing a data entry clerk, I should use RULA. If I'm analyzing a physical therapist, I should use REBA.
Correct. Using the wrong tool gives you bad data. If you use RULA on a guy carrying boxes all day, you'll completely miss the stress on his legs and lower back. If you use REBA on a typist, you might miss the subtle but damaging nuance of their wrist deviation.
This feels like a good moment to sort of bridge the gap to the wider world. We've mathematically perfected the lift. We've analyzed the posture. The angles are right. The weight is low. But then chapter 25, the construction safety chapter in the same book, throws a wrench in the gears.
The environmental wrench.
Exactly. Because we aren't lifting things in a sterile, perfect lab. We're lifting in the real world. I want to talk about environmental ergonomics because the source material in chapters 25 and 30 hints at how the environment itself attacks the worker.
This is so critical.
Yeah.
You can have a perfect lifting index of 0.5, but if the environment is hostile, the math completely breaks down. Take something like static electricity.
Which seems like a minor annoyance, right? A little zap.
In an office, maybe. But imagine you are carrying a volatile chemical or even just a heavy load on a construction site. The air is dry, you build up a static charge, you go to touch a metal railing, zap.
It's startling. It makes you jump.
It triggers an involuntary muscle contraction, a jerk. If you are under a heavy load, say holding 40 pounds, and your muscles violently contract because of that shock, you can tear a muscle or drop the load instantly. The entire ergonomic calculation assumes smooth, controlled movement. Static shock introduces chaos into that system.
The text also brings up vibration, specifically with manual tools in chapter 30.
Hand-arm vibration syndrome, or AVS, sometimes called white finger.
This has to change the math of the coupling multiplier, doesn't it?
Drastically. If you're holding a jackhammer or a powerful grinder, the vibration starts to numb the nerves in your hands. You lose that tactile feedback. So what do you do to compensate?
You squeeze harder.
You squeeze way harder just to make sure you don't drop it. You overgrip. This spikes the muscle tension all the way up your forearms and into your shoulders. Plus, the vibration itself is doing direct damage to the capillaries and nerve endings over time. So a tool might only weigh 10 pounds, but if it's vibrating heavily, the ergonomic toll on your body is equivalent to holding 30 or 40 pounds steady.
It creates this false sense of lightness because your hands are numb.
Exactly. And let's not forget the tools themselves as levers. Chapter 30 talks about things like pry bars and shovels.
Which brings us right back full circle to the horizontal multiplier.
A shovel is just a beautifully designed machine to extend a load as far away from your body as physically possible. It is an ergonomic nightmare by design.
You are intentionally maximizing the fulcrum penalty to get leverage on the dirt.
You are. Which is why the technique with a shovel, keeping the load close to your body, using your thigh as a pivot, is really just a desperate attempt to hack the horizontal multiplier. But ultimately, construction environments are where the perfect math of the office meets the chaos of mud, vibration, and electric shock.
It really highlights that safety isn't a simple checklist. It's a system. You can't just fix the lift. You have to fix the air by controlling humidity for static, you have to fix the tool by getting one with vibration dampening, and you have to fix the ground to make sure it's stable.
It has to be holistic. If you ignore the environment, the NIOH equation is just a theoretical number on a piece of paper.
So we've unpacked a lot here. We've gone from the 51-pound absolute limit to the geometry of the twist, to the scoring of office posture, all the way to the chaos of the job site. If the listener takes one big thing away from this whole deep dive into Chapter 24, what should it be?
I think the biggest takeaway is that injuries are not accidents. That word implies unpredictability, randomness. But when we look at the lifting index, or we look at a RULA score, we see that injuries are actually design failures.
We are designing jobs that make people get hurt.
If a job has a lifting index of 3.0 and a worker eventually blows out a disc in their back, that wasn't an accident. That was a mathematical certainty. We predicted it. And because we can predict it, we have the moral and the professional obligation to prevent it.
By changing the design, not by trying to change the person.
Exactly. We stop looking for tougher workers and we start building smarter workplaces. We move the shelf. We buy the hydraulic lift table. We enforce the move your feet rule. We make the math work for our biology, not against it.
I want to leave everyone with a final thought that's just been nagging me since we talked about the asymmetric multiplier, the twist.
The 90-degree penalty.
We talked about how twisting 90 degrees robs you of nearly 30% of your strength. And I've just been sitting here thinking about my own day. How many times I twist to grab my phone off the charger, or reach back to grab my bag from the passenger seat, or turn to talk to someone while I'm holding a cup of coffee.
It's constant, isn't it?
It is. And it strikes me that we do it for efficiency.
Yeah.
It feels faster to just twist your torso than it does to swivel your chair or move your feet a few inches. But the math proves that this so-called efficiency is a lie. We are trading long-term structural integrity for a millisecond of time.
We are paying a tiny tax on our discs every single time we refuse to move our feet.
That is a haunting image. A tax on our discs. So,
Okay.
for everyone listening,
Yeah.
the next time you reach for that laundry basket, or you're loading the dishwasher, or you're just reaching for a stapler at your desk, do the invisible math. Where are your feet? How far is the reach?
And for the love of your spine, don't twist.
Pivot, people, pivot. Thanks for taking this extended deep dive with us into the mechanics of your own body. Hopefully we saved a few backs today.
Stay safe out there.
We'll see you on the next one.